Hello, today we're going to do this scary looking limit of an integral. So obviously we've got some infinity business going on here, some infinity times zero. Let's see how we can deal with this. So actually we're just going to ignore the fact that this is a limit for a while, and we're just going to get started with this normal integral. Well, it's not really too normal. It's not like it's an easy integral whatsoever. We're going to start by writing this as the limit as n goes to infinity of n times the integral from 0 to infinity, and then of sine of x to the power of minus n. So the substitution we're going to make is going to be a fairly basic one. We're going to make x to the power of minus n equal u, and that means that x equals u to the power of minus 1 over n. So that's just from bringing that or raising that to the power of minus 1 over n. Now also we need to calculate the dx. So let's see. We're going to get minus n times x to the power of minus n minus 1 dx equals du. So that's fairly basic. Now plugging it in like this is going to give some problems. We want to figure out dx, and maybe we want to express our coefficient here as something in terms of u, so that of course we get an entirely u integral. So that's why we actually made x into a clean form. So we're going to get minus n times u to the power of minus 1 over n to the power of minus n minus 1 dx is equal to du. So notice all we've done there is we've plugged this x into here so that we can get an expression for dx all in terms of u. So let's maybe combine these exponents. So we're going to get minus n times u to the power of 1 plus 1 over n dx equals du. Now let's convert this into a singular fraction, so we're just going to get n plus 1 over n. So this means dx equals minus 1 over n times u to the power of minus n plus 1 over n du. So that's just from bringing everything on the left-hand side over to the right-hand side by dividing. Now we're almost ready to plug this in. So maybe let's get rid of this and let's see what happens with our bounds. So let's see what's going to happen here when x tends to infinity. So we're going to have to take a limit here quickly. It's not too difficult. Just to see what happens when x goes to 0, because obviously you can't divide by 0. Now notice that our exponent doesn't really matter here, it's just a very positive number. We're going to ignore it for now, although it gets kind of tricky, but we're going to see when x equals 0 from above, because we've got this positive interval, we're going to get positive infinity. Then secondly, when x equals infinity, so let's see, limit as x goes to positive infinity of 1 over x to the power of n. Well, that's clearly going to give us 0 because we divide by a very, very big number. So let's maybe get rid of this and rewrite some stuff. So we've got everything set up for a substitution, and we're going to get the limit as n approaches infinity of n times the integral from, and then we need to change our bounds, from infinity to 0, so that's what we just looked at, and times sine of u, so that's just plugging in our substitution, and also dx is going to equal minus 1 over n times u to the power of minus n plus 1 over n, and then all du. Now let's clean this integral up a bit. So there's a lot of stuff we can do here. So first of all, we can take this minus sign and make it a plus sign and switch the bounds of integration. So we're going to get from 0 to infinity again. The second thing we can do is we can take this times n and dividing by n and scratch those. And then lastly, we're going to rewrite this integral slightly. The limit as n tends to infinity of the integral from 0 to infinity of sine of u over u to the power of n plus 1 over n du. So let's see, we've got this pretty complicated limit here and actually integral as well, but what happens to this exponent here when n tends to infinity? So basically, a way to see this is if we divide this through, and we're going to get u to the power of 1 plus 1 over n, so that's the same thing. We can see that when n's to infinity here, this is going to be 0, so in the end, we're just going to get dividing by u, and then we can get rid of this limit. So fantastic, we've now got this integral and we've got rid of our limit completely. Now, what is this equal to? Many of you might know this actually, but if you don't, definitely I'm going to solve it anyways. I have got a video about this, or slightly harder version of this, already on my channel. I'll link it down below. But I'm going to do the solve right now. If you do know the result for this already, again, skip this, or maybe look at the harder version of this, which is definitely interesting as well. Let's see what we have to do to solve this. So let's see, how do we do this? So we've got this integral set up. Now, we're going to make this a function of, let's say, a. So f of a is going to equal the integral from 0 to infinity of sine of u divided by u, and then we're going to do something special here. We're going to introduce a new piece in this function, which is going to be e to the power of minus a times u du. Now this might seem strange because we've just introduced this new part of our integral, which doesn't really seem to belong there. Now notice that if we take f of 0, we actually get this exponent 0, which means that e to the power of 0 is equal to 1. So that actually equals the integral we need. And this way we can work with this as a function of a. Obviously u isn't a variable here, so we can't actually work with u, and we need to take a as our variable. What are we going to do with this function? So you might have seen this trick before. This is Feynman's trick. We're going to differentiate it. So f, or f prime of a, is going to equal the integral from 0 to infinity, so we're just ignoring that this is an integral, minus, because we're going to differentiate with respect to a here, very important that you get that that is going on, times u times e to the power of minus a times u du. So this minus sign comes from the chain rule of differentiating e to the power of minus a times u, and also that's the same thing for the times u, also from the chain rule. Now obviously we can cancel out this over u and times u, and so we're going to get this new integral, which is actually quite doable. We can do this using partial integration, and we actually get a closed form for this. So let's do that. So we're going to get our table set up. So let's see. This table obviously has a sign column, so this determines the sign of our multiplication. So that's just going to be 1 minus 1, 1 alternating forever. Then we've got this differentiating column where we're going to get e to the power of minus a times u. And actually, let's include this minus in this function, so we don't need to worry about distributing that at all. And then also let's integrate sine of u. Now let's see. We're going to have to do this process repeatedly. So in the first derivative of this function, we're going to get a, and let's notice that we're differentiating with respect to u here, also quite important, a times e to the power of minus a times u. So that's just, again, using the chain rule. Then we're going to get minus a squared times e to the power of minus a times u. Also, differentiating or integrating sine of u, we're going to get minus cosine of u and then minus sine of u. So if you want to check that, you can just differentiate in this direction or integrate in this direction if you're aware of how to do this. So how do we actually read this table? Well, we read it diagonally until we want to stop reading it, and then we take a horizontal integral. Now all the diagonal ones we have to evaluate as well. So let's do that. It'll be clear if you don't actually know the DI technique for integration by parts, but let's see, what does this give us? So we multiply by our constant in front and we read it diagonally. So we're going to get, let's see, we've got two minus signs, so that's going to give us a plus sign, e to the power of minus a times u times cosine of u, evaluated from 0 to infinity. Then secondly, we're going to get this second part, so we're going to multiply by minus 1. We're going to read it diagonally. Again, we've got two minus signs, so those are going to cancel. We're going to add the a times e to the power of minus a times u times sine of u evaluated from 0 to infinity. And then lastly, we're going to have to add in this integral horizontally multiplied, but let's do that in a moment. First, let's get rid of or deal with these constant terms here. So let's first look at this evaluation. So let's see what happens when u tends to infinity. When u tends to infinity, this exponent is going to be vital. That exponent is just going to crush sine of u, and that expression is going to go to 0. Let's also see what happens when when u is 0. Well, sine is going to be 0, and this exponent is going to be e to the power of 0, which is 1. So in essence, this whole thing is just going to be 0. Now, secondly, what happens to this evaluation? When cosine u tends to infinity, we're going to have the same story. We're just going to have the dominating exponential function here, or to the power of minus infinity, is just going to give us 0, and that's going to dominate cosine. Now, what happens when u is 0? So let's see. We're going to have cosine of 0, which is 1, and then e to the power of 0, which is also 1. So in essence, we're just going to get minus 1. Let's see, the minus actually comes from this being the lower bound of this evaluation. So let's get that. So we're going to get minus 1 plus our integral from 0 to infinity, and then a squared times e to the power of minus a times u sine u. So again, notice that these minus signs have cancelled in this horizontal row. Now let's get rid of this table, and let's actually examine our integral real quick. So let's see what parts are similar maybe, so that we can do a trick. So this integral contains that function of u, and actually of a as well. And here we've got the exact same function. And let's also notice that a squared is actually just a constant with respect to u, so we can write this integral as a squared times the integral from 0 to infinity. Now, as I just said, this entire part is just the exact same, but there is this minus sign, which is different from our f prime of a. So let's see what that actually gives us. We need to take that minus sign into account, so we're going to get minus 1 minus a squared times f prime of a. Now, using that result, we'll get this simple expression for f prime of a, or the derivative of f. So f of a, or f prime of a, is going to equal minus 1 minus a squared times f prime of a. Now let's solve this for f prime of a. Nice, so we've got this expression for the derivative of f. Now we actually needed just f itself to be able to evaluate it at 0, right? So how are we going to do that? Well, a derivative and an antiderivative are obviously opposites of each other. So we're going to take the antiderivative, which is going to be f of a is equal to minus the antiderivative of 1 over 1 plus a squared dA. So again, this is just taking the antiderivative. There is no bounds here because it's not actually a definite integral. It is just taking the antiderivative to be able to get to this all-important f of a. Now let's see, this is also a pretty standard integral. This integral is equal to minus arctan of a plus c, of course. Now you might think that we're basically there, and we are, but we do have this massive issue here. We've got this plus c. So if we plug in f of 0, or we plug in 0 into f of a, this will be 0, arctan of 0 is 0, but then we still have this c. So we need to figure out what c is. Now how can we do that? There's actually a really clever trick to be able to do that. So let's see. we're going to take a limit. So the limit of f of a as a goes to positive infinity. So f of a. So this is going to be equal to the limit as a goes to infinity of minus arctan of a plus c, but also equal to the limit as a goes to infinity over integral from 0 to infinity of sine of u over u times e to the power of minus a times u du. Okay, so what can we actually take away from this? Let's see what happens here in this integral. So this is quite important here. Again, we've got this exponential function, just like in our evaluations from the partial integration. We're going to get this dominating term, which is just going to make everything in this integral 0. So this entire thing is equal to 0. Now next up, we've got this arctan function. And as a goes to infinity, we're actually going to get arctan equals pi over 2, or the entire function here equals minus pi over 2 plus c. So take a look at if you understand why arctan of infinity is pi over 2, and let's get this in. So we've got that minus pi over 2 plus c is equal to 0. Now this obviously means that c is equal to pi over 2. So we can plug this in here. So arctan, so minus arctan of a plus pi over 2. And we've now got our function, and we can now evaluate this at any value we want. So we could just get a load of other very interesting integrals from this. We've got this entire family, but f of 0 is now minus arctan of 0 plus pi over 2. Arctan of 0 is equal to 0, so this is pi over 2. So again, amazing integral. We also solved this classic one. Often people would probably just stop here because they know this integral, I guess. But also if we look back at what we actually came from, this crazy limit, which is actually pretty hard to solve, and we actually just did a simple substitution and then came to this classic, which was pretty hard, which made the video a lot harder than it might actually be if you just know this classic here. Let's see. I hope you enjoyed this integral. If you've got any tips for me, definitely let me know. And maybe if you want to see the more difficult version of this integral as well, you can look it up on my channel. It was one featured in the MIT Integration Bee as well, just like this one. And in general, these integrals are pretty difficult, quite amazing. And yeah, thank you so much for watching. Till next time.